coordinator. So if ever maybe you might have questions, you raise your hand, then she will liaise with me, and then we can help you. Or else, if you want to make a comment, you can also raise your hand, then unmute your mic, and then you make your comment. Maybe before we start the session, Bulelwa, would you like to maybe say something?
Thank you, Mr. Ngcobo. Good morning, everyone. Now, it is to just remind them of the ground rules, name. And I
Okay.
think one of them you've already mentioned about the mics. And the recording, I've started it from my side, and there are cameras. I think the last session we had an issue with the camera. Just please make sure that your cameras are switched off and your mics are off unless you are recognized, or like what Mr. Ngcobo was explaining, that if you have a comment or you want to say something, then you can unmute and talk to him. Thank you, Mr. Ngcobo. You can proceed.
All right, perfect. Thank you. So yeah, today's session is based on chapter 7 and 8, where chapter 7 is just mainly looking at confident intervals. Hope you can see my screen. I'm sharing my screen. So yeah, before we go into depth of what confident intervals are about, and hypothesis testing is about, which is chapter 8, let me sort of give you guys some interest, right? Why is it important to know confident intervals? So, I mean, the main understanding of statistics, just from first base level statistics, is that we always want to make some conclusion based on the population, right? We always want to make assumptions which are really of exact value of that of what's happening in the population, right? So any guess you make, you always want to be correct. So then stats comes in to make sure that whatever your choice of guess, whatever you claim, is somehow close to what is referenced by the population, right? Now, confident interval, it sort of give you now an interval of your statistic, which is what you calculate based on the sample. So it gives you an interval of your statistic, which will reference your population parameter. Now, let me make an example of this. Let's say you want to buy me a present, right? So in buying me a present, you want to buy me a present which is very much correlated to my how old I am, right? My date of birth, right? Okay, so in wanting to do that, I mean, you can't buy me then a kiddie's present. You want to buy me which is in line with my age. So you can't buy me a kiddie's present, but you don't know my age, right? You've never asked me my age. Um, you also can't buy me an older, I mean, grandfather's present. Also, I mean, right? You also can't buy me sort of youth bracket kind of presents because you don't know my age. But let's just say, lucky enough, you know people around me, right? You don't have my number to call me, but you have numbers of people around me. Um, you then make an assumption. You say, okay, I've heard this guy's voice. Probably this guy is 25, right? You make that assumption, right? Now, someone who never done stats will just assume that I'm 25 and go to the shop and buy a 25-year-old present, right? The risk of that is that you might waste your money because you might buy a wrong present for me because I might not be 25. I might be greater than 25 or even less than 25 years, right? So your probability of buying the wrong present is high and it's not calculated. That's someone who doesn't know anything about stats will just take the assumption of that I'm 25, go to the shop, buy a present of 25, send it to me, right? Probability of you being incorrect is higher, or else it's just not calculated. Now, let me tell you what a person who understands stats will do. The person who understands stats will have the assumption of me being 25 and ask the people that I'm close with, maybe 5 of them, my age, right? Also, the people that you think I'm close with might not know exactly my age, but can give you sort of an estimate, right? So me, my age that I know of is the actual parameter. Take that as like some sort of a population, right? I know my age. You ask 5 of my friends or whoever that might know me, then they'll be like, no, this person is 20. Some say, no, this person is 30. Some say 26, 27, 28, right? Look, what you've just done there is to sort of, collect your own sample, right? Now, you have now 5 different age, which are of estimate to my actual age, right? I'm trying to give you guys interest of this. Now, what you from these 5 different age that you've got, you'd want to find the average, right? Remember the formula for average. I mean, it's your summation of xi divided by n. You find that, right? Then you have your average. Your average now is your statistic because it was calculated just on 5 of my friends, and I have a lot of friends, not just 5. So you have your statistic, right? Your statistic is, you're trying to estimate my parameter, which is my actual age, right? So having this 1 point statistic, which is the average of calculated out of this 5 different age, is not good enough. You rather buy a present within an interval of age where you will say my age might not be 25, but you show that my age is around 20 to 30, right? So if you're buying a present, you've done stat now. This is someone who've done stat. When you're buying a present, you'll buy a present which is within the age group of 20 to 30, because you know that in some way or another, this guy, from the information I got, his age is between 20 and 30. So it's better to have a conversation of intervals if you want to estimate a parameter than having 1 point estimate. Because once you cater for a group, an interval, you somehow show that your parameter, which is the actual value from the population, is between this 20 to 30. Then I'm sure, if you buy me a present between the ages of 20 to 30, you can find something that would relate to my age there, right? Now, chapter 7 is looking at how sure are you? How do you construct this confident 20 to 30 years, right? Okay, hope that long example did make some sense to you guys, to have interest? Right. Now let's look at this. You've got population, right? In population, you have things called parameters. In our case, we're only going to look at 3 parameters, right? A parameter is anything calculated based on the population. It can be your mu, right, which is average. It can be your proportion. It can be your variance, right? Then obviously we both agree that it's very difficult to know information about the whole population. We rather get the sample. Now, the sample, it's either you use probability-based sampling methods or non-probability-based sampling methods to get your samples. From those samples, you then have estimate of these population parameters. Now, an estimate of a mean or an average population average is called X bar, right? An estimate of proportion is P hat. An estimate of variance is denoted as just S squared, right? All these, the reason you're collecting all these or you understand all these, it's because you want to do something referred as statistical inference. Statistical inference is a situation where you have your sample. From your sample, you want to conclude based on the population. What do we call that? We call that statistical inference. Okay. Now I've explained that chapter 7 is estimations, confident intervals. Then chapter 8, we're going to look at hypothesis testing. Right? Now, my example of age, I've also explained it here. Right? So we rather have what is called an interval than just 1 point estimate. Now, in our interval, we'll want to include an error because an interval also can have an error, right? But what do we want to do from that error? We want to make sure that we minimize our error as much as possible so as to just be sort of accurate in understanding that within our confident interval, there is this actual parameter of which in our case, it was my age, right? Now, how do we, so the first question is, how do we then choose the error, right? The second question is, how sure are we that within this interval, my age is here, in considering also the error? Okay. Are you guys still with me? I'm really trying to go as slowly as I can just to make sure that you guys understand each and everything. Are you guys? Give me a thumbs up if you are. All right, cool. All right, thank you. Right now, confident interval for average. So we're going to look at 3 things, like I've said. We're looking at average population, average, finding the confident interval of that. We're looking at proportion, trying to find the confident interval of proportion. We're also going to look at variance, trying to find the confident interval of variance, right? Okay. So for confident interval, where you want to find the confident interval of average, where this is known, your variance is known, right? I'm not going to go through this because you guys don't do any proofs. This is the formula we use, right? This is the formula we use. Let me try get something. This is the formula we use to find the confident interval of what? Of this guy, mean, right? This is the formula we use. Within this formula, you see your x bar is here, plus or minus. This is your error. So this is what we use to sort of construct our error, right? Now, how confident are we that our population average is within this interval? We are 1 minus alpha sure, right? So this is our confidence. All right, I want to draw something. Can you guys see my drawing from a side? Give me a thumbs up if you do. I just draw a line on. All right, cool. So I want to make something now. So you know the actual parameter, right? My actual age. It's in the middle here of this ball shape. Why did I make an example of age also? It's because age is a continuous variable. We're still looking at continuous variables, right? So you have your estimate. Estimate 1, x bar. You have your estimate 2, x bar. Now within x1, x2, this interval, how sure are we that our actual parameter lies within inside here? Then the answer to that, I'm 1 minus alpha sure, right? That my actual parameter, which is mu, is within this, in considering my error, which is this guy. Let's look at an example. A customer call center in a large company wants to test the listening skill of its employees by running an experiment on a sample of n, which is 50 in this case. The experiment involves reading a passage of information to them and then giving them a test based on the content. The average mark of employees was 10. Average mark, right, is x bar. That's your x bar. It's 10 out of 15, and the standard deviation is 5, right? So you are being told here the standard deviation. If the standard deviation you're being told is the same thing as giving you the variance, because the standard deviation square will give you the variance. So in this case, variance is known, right? Now, what do they want? Construct a 90% and 95% confident interval for the population. So we'll start with 95%. What does this mean? It means that they want you to construct a confident interval whereby you are 90% confident that your actual parameter is within your interval. Right. Okay. Now, how do you do that? The first thing you do is you say, okay, you want me to construct a 95%, a 90% confident interval. So it means 1 minus alpha in my case is what? 0.9. Right? Now I know that the formula to use is x bar plus or minus z 1 minus alpha by 2, then your standard error, right? Why do we divide by 2? Because you've got two estimates in an interval. Now, guys, if 1 minus alpha is equals to 0.9, what is my alpha? You tell me. Someone unmute and tell me this nice thing. If 1 minus alpha is equals to 0.9, what is my alpha? Anyone? So 1 minus alpha is equals to 0.9. What is my alpha? It's a simple mathematics transformation here. If you know that 1 minus alpha is equal to 0.9, then your alpha is equal to what? Let me also get my calculator. Yeah, anyone who wanna try it out? 1 minus alpha, it's 0.9. What is then my alpha? Come on, anyone? All right. Okay, let me just give light then. So 1 minus alpha is 0.9. Alpha is equals to 1 minus 0.9 is 10%, right? So it's just a complement of this, right? I mean, give me a thumbs up then if you understand now. Okay, cool. Thank you. So, yes, question. I love questions. Yeah. Or are were you trying to give me a thumbs up? Mapule. Okay. Oh, a thumbs up. Okay, cool. Yeah, so it's 10%, right? Then you come here now. Now I want you to, in your calculator now, I want you to do this for me. 1 minus 0.1 over 2. Remember, this 1 is on the side, so it's 1 minus 0.1 over 2, not 1 minus 0, 1 all over 2. This is wrong. Do this. 1 minus 0.1 over 2. What's the answer?
It's 0.95.
0.95. Thank you, sir. Thank you, sir. Right? 0.95. Okay. Now, what's your X bar? Your X bar you were given as 10 plus or minus. You go to your tables now. Let's quickly go to our tables. I just hope that just statistical tables. Hey, these tables are always giving me a hard time. Statistical. All right, got them. Okay. You go to your Z tables, your standard normal tables. Where is that? Where is that? Where is that? Right. So you said what? What's the answer there? It was 0.95, right? 0.95 is here, right? You look at your selected percentiles in most cases. So 0.95 is here. Then I want you to take this value now. 1.645. 1.645. Where is this? 1.645, right? It's here. Then 5 over the square root, the 5 you were given. It's your standard error. The square root, the 50 you were given. Then you put this in your calculator, you find your interval. What does this mean? We are 90% sure that the average mark for all employees will be between 8.8 and 11.2. Right? We did not only conclude on what I want you guys to see here. We did not only conclude on just this 50, right? We concluded out of all the employees, right? So what does this mean? It does not necessarily me as an employer to go through each and every one script, but now I understand that most people would get marks between 8.8 and 11.2, right? In a test which is out of 15. Now this also give me an idea that no, my employees understand whatever that I was trying to test, the listening skills. Okay. Did you guys understand now the narrative, the good narrative of this? Two, are you guys able to put this in your calculator and find this 8.8? Any questions? If you guys understand, give me a thumbs up. Okay, okay. So Mapule, you're the only one understanding. If you don't understand, just unmute and tell me that. Maybe can I then go through this example again? You know, because the point of these sessions is just to make sure that you guys understand each and everything I'm gonna be presenting to you. So I'm assuming you all understand. All right, perfect. It's nice then.
Sir,
Yes.
just on
Yeah.
that 1 point, I think I'm lost from the point where you got 1.645.
All right.
So we get the Z. Is that a number? Are we always going to get it from the table that you went to, from the Z
Yes.
that we got?
Yes. So do you
Oh,
understand how we got this one?
which one?
0.95.
Yes, yes,
Okay, good. Then we take this 0.95, we go to our tables. Then from our tables, there's your 0.95, then 1.645 is there.
Oh, let's go back. I think I thought that zero. So the 0.95 is not from the 95% that we are given.
No, 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 no.
Not. Oh, let's go back there then. I think I'm.
Okay, so
Okay.
the first thing, don't mute your mic, ne?
Yes.
Right. So the first question I'm looking at here is constructing a 90% confident interval. I haven't looked at this one,
Yes. Yes.
right?
Oh. Okay.
Right.
Yeah.
So now the first thing then I need to understand is that I need to use this formula to calculate the confident interval, right?
Yes. Yes.
Okay. This is the formula, right? This is the formula. Now, the
Yes.
next thing then I need to do, I need to know my alpha. I know that you want me to calculate a confident interval where I'll be 90% sure that my actual parameter will lie within this interval, right?
Yes.
So, yeah, then you say 1 minus alpha is equals to 0.9, which is your 90%, right?
Yeah. Which is the piece in between on the graph that you've drawn?
Yes, which
Yes.
is the area between
The area.
my
Yeah.
two intervals, right? Okay,
Yeah.
cool. Then if 1 minus alpha is equal to 0.9, then my alpha is then just 10% of, you know,
Yes.
do you understand me
Yeah. Got it.
there?
Okay.
Okay, cool.
Yeah.
Then I said to you, do this for me in your calculator. You have your calculator with you there.
No.
No. Oh, okay. But what I want you to understand is that if you take your calculator and say 1 minus 0.1, which is your alpha, divided by 2, you will get 0.95,
Yes. Okay. Now I got it now.
right?
Mm.
Then you then do that thing of going to the tables. Then from the tables, you'll find your 1.645.
Yes, sir.
Did we share some light? Are you okay now?
Yeah, I'll just follow it. When we do the 95, I just want to
Yes.
try it. If we do the 95 and I'm still stuck, I'll talk.
All right, cool, perfect. So now we're doing the 95, right? Now Yes, question.
Yes, sir. With
Yes,
regards
sir.
to the 8.8 and 11.2, I see the 8.8 is from the minus and the 11.2 is from the plus when we
Okay.
do on the formula there. So is it a requirement that we start with the minus or we start with the plus so as to ensure that the parameters are so the smaller parameter will be the first one and the other one will be the larger one will be the last one. So we start with the minus and then the next one will be the plus.
Yeah, I mean, in sort of logical sense, you'd want to have an interval that start from the minimum value to the upper value, right? Your upper lower limit. This is called your lower limit. This is called your upper limit, right? So the minus will always be this side, then the plus will be on this side.
Cool. Thank you.
All right, perfect. Okay, let's look at the 95 now. So you are given same formula, same everything. Alpha 1 minus alpha is equals to 0.95, right? So what is then my alpha, guys? You tell me. If my 1 minus alpha is 0.95, which is what I'm given, then my alpha is what? You tell me.
Is it not 0.05? 0.05?
Zero, what? Say that again. 0.05. Is that what you said?
Yes.
All right, cool. Why are you saying it's 0.05? What did you do to
I don't
find
have a
this?
calculator, so I'm just checking. It's 1 minus the 0.95.
Oh, I know. You're on the ball here. That's good. Right? Now, you need to then say 1 minus 0.05 divided by 2. If you put this in your calculator, what answer do you get there? 0.05 divided by 2. What are you getting, guys?
0.975.
All right, good.
Okay, just this. Why are
Yeah.
you saying 1 minus the alpha over 2? Are you going back to the original formula?
Yes, you see this formula.
Hmm. Yeah,
I'm
so you're
doing
going
this
back there.
because yeah, I'm going to the everything I'm doing, it's because I want to plug in some things with to this formula.
So that thing is not Z1. The one is big, it's on its own.
It's Z, this is Z1 minus alpha over 2, which is what you're doing here. So this value, it's
Oh.
actually Z 0
Oh.
975.
So
Then you
now
go
I get.
to then you go to your tables. Where is 0.975? Oh, okay, it's here. Then I need 1.960. Go straight to this thing. What do you need? 1.960. Okay. Are you given this? You given this. You are 95% confident that your actual parameter average is between 8.6 and 11.4. Are we clear? Do you guys understand now? Perfect, perfect, perfect. We are very sure that it is. Let me see. Let me see. Okay. Do you see if you increase your confident interval, you making if you increase your yes your thingy your confident of significant, right? So your 1 minus alpha, if you increase it, you're also increasing your interval. So it becomes a bit wider, right? If you decrease it, you narrow it, your confidence interval, you narrow it. Okay. All this, what we were doing, we were looking at situations where your variance, your standard deviation was known. Now, there are situations where your standard deviation or variance can be unknown. What do you then do? If your standard deviation is unknown, right? You replace your standard deviation with an S squared, or your variance squared. The only time that your standard deviation or variance will be unknown, it's when you are given variance or standard deviation based on the sample, not on the population. Then your standard deviation or your variance will then be referred as unknown. Right. If your sample size, now your variance, your standard deviation is unknown. If your sample size is less than 30 or equals to 30, you will use something referred as t-distribution, right? If your sample size is greater than 30, your variance is unknown, you will just change your variance to call it S, but still use your Z tables. You guys don't do proofs, so this is what you guys need to know, this formula here. I'll give you a nice formula sheet, which is sort of detailing everything here, every formula, when to use this formula, how to use this formula, right? After the session, right? I'll just, make notes for you guys for this confident interval formulas, right? Now, this is what I want you guys to see here. We use this formula if our sample size is less than 30. So as you can see here, it's no longer Z is your T distribution. We still use the same understanding of the significant alpha, where we're looking at 1 minus alpha, right? Confident interval for the population mu. Your variance is unknown, so we use this formula here. Let's look at the example. You randomly select a sample of 20. Now, just from this, you can see that your sample size is less than 30. Mortgage institution, and determine that the current mortgage interest rate expressed as a percent at each. The mean rate is 6.93 with the standard deviation of 0.42. Guys, this standard deviation is not from the population, so the variance, the standard deviation, is unknown, right? They want you to construct a 95% confident interval for the actual interest, right? Which is your average. What do you then do? Let me draw. The first thing you do is what? 1 minus alpha is equals to 95, 0.95. What is your alpha then? You guys tell me. If my 1 minus alpha is 0.95, what is my alpha? Talk to me. Anyone. Just tell me alpha, please.
0.05.
Thank you, Mapule. 0.05, right? Now, all right, then, Mapule, do you have your calculator with you there?
Yeah.
Then please
I
do
do.
this.
Yes, I do.
Okay, perfect. Please do this for me. Say 1 minus 0.05 divided by 2. What are you getting there?
0.975.
Oh, thank you, thank you, thank you. 75. What do you, now we need, where should we look for this now? Do we look for it in the T distribution table, or do we look for it in the Z distribution table?
In the T distribution table, since it's less than 30.
All right, cool. I mean, what else, man? It's just less than 30. Is there any other reason we might go to the T distribution?
We don't have the what you call it,
Population variance.
yeah, yes, the population variance. We only have, yeah, so we need
It's
to go
unknown,
there.
right?
Yes.
All right, cool. Right, thank you for that. Then I go straight to the T distribution. Right? Where is 0. You said 0.975, right? Did you guys say that?
Yes.
Okay, cool. Then what are your degrees of freedom? So to find your degrees of freedom, it's n minus 1. So it's your sample size minus 1, right? What are your degrees of freedom in this case? You guys tell me.
19.
19. Perfect. 19. Okay, 19. 19. Go to my tables. Where is 19 here? This is 19, right? Do we agree? This is your 0.975. Where do these guys meet? Here. 2.093. 2.093. Right? Everything else is the same. You are given this plus or minus 2.093. You have this, you have the square root of 20. Good. You can say with 95% confident that your true average interest rate is between 6.93 and 0.42. Right. This can also be represented in a percentage form where you have your 7% and your 0.42%, right? Okay, any questions? Clear. If it's clear, give me a thumbs up. All right, good. Let's look at this second example. You randomly select 50 now. It's no longer what? 30 or less than 30, 50. Institute and determine the current mortgage interest rates at each. The mean rate is this, the standard deviation is this. Construct a 95% confident interval. The first thing you do is what? You do that thing, 1 minus alpha is equals to, this is equals to, this is not z, but might as well erase, but I don't want you guys to get confused. Doesn't want to erase now. Oh my god, what did I just do here? Okay guys, my system is failing me now. I don't know what I just did here. We'll be back. Okay, we're back. I'm so happy that you guys are following, because we're gonna need this information in chapter 8, you know. Right, so 1 minus alpha is 0.95. Then your alpha is then 5%, which is 0.05, right? Then, I mean, we both agree that you need to change this and call it S because it's from the sample. Otherwise, if it was a variance from, it was a standard deviation from the population, you were going to denote it with this. But because it's from the sample, you just convert this and call it S. Now, if you put this in your calculator, alpha by 2, what are you doing? You're going to get 0.975. We both agree, right? Now, instead of going to the T distribution table, you go to the Z. Why did you go to the Z? Because your sample size was greater than 30. Do the same thing, everything, right? Any questions? Okay, cool. All right. Now, these are our notes now. This is what you need to understand. As you increase the sample size, the confidence interval gets narrow. Guys, let me ask you a question. From the first example I made of my age, who is better off guessing a right interval age of mine from a person who will ask 5 of my friends than a person who will ask 20 of my friends? Who's better off getting a better interval of my age between these two people? Someone who asked 5 of my friends or someone who asked 20 of my friends? Hello? Guys, anyone?
I would suggest that if the one who asks more of your friends, because you get to eliminate more possibilities than the one who asks 5 of your friends.
Okay, cool. That's good. That's good. Yeah. So what does this mean? It means that as you increase the sample size, the confidence interval becomes narrow. So the more close you can be in your actual parameter, right? Narrow means we're coming close to you. We're coming close to the actual parameter, right? This makes sense because a small sample only represents a small portion of the population. So you can't be too sure about the estimate. The larger the sample means that you are working with more of the population, meaning your estimates are likely to be more accurate. Okay. Right. What do we have here? Now, we've done the average, the X bar, right? Confident interval. Now let's look at finding the confident interval of this guy. Okay, I'm still drawing of this now. Variance. Once a question comes into play and you're trying to find the confident interval of variance, you need to understand for you to find that confident interval, you need to know your chi-square, right? Your chi-square formula. Variance chi-square, variance chi-square, right? Now you guys don't do any proofs, so yeah. So this is the formula you use, right? We're still looking at the same confident significant level where your 1 minus alpha, but now the formula we now look at is this one, where you have your n minus 1 times your variance, which is of the sample, hence your S, right? Over the chi-square, right? And your degrees of freedom, which is your n minus 1 and your 1 minus alpha squared, right? This is your lower bound. This is called lower bound. I'm going to call it L. This is called upper bound. I'm going to call it U, right? Please note that this side, whatever you're going to put here, is not equals to what you're going to put here. These are two different things, right? Let's look at the example. You randomly select a weight 20 samples of an allergic medicine. The sample standard deviation, right? The sample standard deviation. So what does this mean? This guy is unknown, the standard deviation of the population. So the sample standard deviation is 1.2 milligrams. Construct a 95% confident interval for the actual what? Variance. Because they are interested in understanding the confident interval of variance, straight, I understand that for me to find this confident interval, I need to use a formula of chi-square distribution, right? Do we agree on that? Because of this, I know I need to use this, right? Otherwise, if this was average, I was going to use the same formula that we used previously. Okay, now how do we do this? You do the same thing. You look at this formula. What is your degrees of freedom? Someone unmute and tell me. So your degrees of freedom is your n minus 1. What is your degrees of freedom? It's
19.
still 19. Okay, good. Thank you. Thank you. Thank you. Then what is your 1 minus alpha? You guys tell me.
0.1.
You sure? Are you sure? Are you sure? Are you sure?
Yes.
Your 1 minus alpha is 0.9. You given your alpha, it's 0.1. Right?
Yeah, sorry, I was answering like.
Yes, no, I get it. Don't worry. I can't write here, but you guys get it. It's 0.9 here. It's 0.1 here. Then what is then your 1 minus alpha divided by 2?
0.95.
0.95. Okay. I'm with you guys. I'm also right. 0.95. Okay. All right. Then what is your alpha divided by 2? Alpha now. You tell me, guys. Come on. Don't leave me hanging here. So alpha divided by 2 is what? So there is no 1 minus what? Yes?
Is it 0.475?
No. Alpha divided by 2.
0.05.
Good. Alpha is this. I'm just dividing this by 2.
Oh, yes,
Right.
I did it.
Okay. Why did I do this and this? It's because this formula, you can see this formula wants it. Right? Now, let's go to our chi-square. Right? Table. This is chi-square table. This Swingley x squared is your chi-square table, right? So let's look at the first one first. Your 0, what was it? 0.95, eh? 0.95, yes. 0.95. What was your degrees of freedom? 19. Right? 0.95 is where? Is it here?
Yeah, 30.144.
All right. write that on a side. Let's look at this other one, 0.05. It's what? It's this one, eh? Where they meet. Yes. 10.11, this thing, 7. All right. There might be an error here, but anyways. Right. So can you see where we founded this 30? Guys?
Yes, yes, we can see.
Can you see where we founded this 10 point? Right? 11. So they rounded up. Right. Guys, are you with me here? Just can you see where we got this 80.14 and 10.12? Yes. Give me a thumbs up. All right, cool. Then you are given this, you are given this. Then you do you put that in your calculator, you'll find this and this. That's your answer. What I want you guys to take out of this, why did we use this formula? It's because they were asking us the question based on confident interval for variance, right? Then we use this formula. Okay. Now, we've looked at average, we've looked at variance. Let's look at proportions now. How do you find the confident interval for proportions? Oh, you guys don't do proofs, so we're just gonna go straight to it. This is the formula we use for proportions to find the confident interval for proportions. We still use the same logic understanding of the significant level, your 1 minus alpha. Let's look at this nice example here. A survey was done on a sample of 1016 households, and the following question was asked: have you been to the doctor in the last 2 years? The results are shown in the pie chart below. Yes, those who said yes were 486. Those who said no were 530. Now, p hat is calculated as your x or k divided by n, of which in this case you're interested in those who said yes. So your 486 divided by the whole population. So 530 plus 486 is 1016, right? So you get your value here, your p hat. Your q hat, what is q hat? Why do you need it? It's because it's on the formula there. Q hat is just equals to 1 minus p hat, right? Of which it's going to be 530 divided by 1016. Not that they just look here, but I know for sure that what they did was saying the complement of this, it's 1 minus p hat, right? Now the question is, find a 90% confident interval for the population proportion, right? Why am I using this formula? It's because in this question there's proportion, right, of households that have been to the doctor in the last 2 years. Now, again, 1 minus alpha is equal to what? Is equal to 0.9, right? Then your 1 minus alpha by 2 is then equals to 0.95, since your alpha is equals to 0.1, right? Now, you then, where do you go? You go to your Z tables, proportion, Z tables, proportion, Z tables. You go to your Z tables, you look for this score, and you'll find 1.645, right? Then you just plug into your formula here. You have your p hat, you have your Z score 1.645, square root of, this is called the standard error. So this is your p hat is this, your q hat is this, divided by your n, which is 1016. Then you find your confidence interval. Simple as that. Clear? Right. So that's it for chapter 7. Any questions? All right. Let's. Yes.
Just in conclusion of chapter 7, so we're using the T if the sample is less than 30, and what else?
The variance is unknown.
The variant. Oh, yeah. Thanks.
If listen, if your sample size is less than 30, but the variance is known, you don't use T, you use Z.
Okay, thanks. Thanks.
Do you guys understand that? If your sample size is less than 30, but your variance is known, meaning the population variance is known, you use the Z table to find your Z score, not the T distribution. So that using the T distribution is so much close or related to your sample size being less than 30 and your variance being unknown. But if your variance is known, you can't use your T distribution, you use your Z distribution, even if your sample size is less than 30. Cool. All right. Any questions? Okay. Let's take a 5 minute or 10, rather, 10-minute break. So we'll resume at what, 12, 10, 12. Okay. 10, 12. I want you guys back here. 10, 12. So go grab
Sure.
a drink or anything.
Thank
10,
you.
12. Sure. Okay, hope everyone is back. I'm back. Right. Now we're doing a very interesting chapter, which is chapter 8. So yeah, what I've guys on our chat, I've sort of shared some nice exercise questions that I'd want you to go through, maybe after the session, just to see if were you able to understand everything we're gonna talk about today, which is chapter 7 and chapter 8. Now, so those are questions prepared for you guys. Yeah, just after the session. In your spare time, please do these questions. Otherwise, if there are things you don't understand, you can always ask Bulelwa for a one-on-one session. Then I'll attend to that. My one-on-one sessions are always going to be on Tuesdays or Thursday, right? Okay, cool. Let's look at now hypothesis testing. What is hypothesis testing? Hypothesis testing, this is where you make claims based on your parameters. Then the claims that you make, you want to test if your claims are true, right? Why? Because in most cases, you want to make your claims and conclude based on the population from your sample, statistical inference. You want to do that, right? Now, we're going to look at 3 parameters that we're going to make claims from. It's either your mu, your population average, or your variance parameter, or your proportion, right? These claims, it's either you make a claim of it is exactly equals to, so your sample statistic, whether you say it's exactly equals to your actual parameter, or it's greater than, or it's less than. So these are the 3 rules that our hypothesis test will be based on. Draw. Right. Right. So how do you then go about constructing an hypothesis test? We always assume that the null hypothesis is true, right? Hence equals to, sorry, hence equals to here. We always assume it's true. Okay. This is called your null hypothesis. We denote it as H naught. This is your parameter. In this case, our parameter is theta, right? Then from your null hypothesis, you'll have your alternative hypothesis. Your alternative hypothesis, you're gonna denote it as H1. This will be your parameter. It's either you claim it's greater than, it's less than, or it's not equals to, which means either or, right? Let's look at the examples. Okay, let me make a good example just to put interest in you guys. You want to sell beef curry around your community, or chicken curry. Now, obviously, between these two plates of food, you'd want to cook what most people would like to buy within your community, either your chicken curry or your beef curry. You make a claim, my guy, from the few people you've asked. You make a claim that you're gonna cook beef curry more than chicken, because out of your few people that you've asked preferred beef curry than chicken curry. You make your claim. Now, your null hypothesis is what? People love beef curry. That's your null hypothesis. Your alternative is people don't like beef curry. So what is that? Your alternative. So it's either people love beef curry or people H1, yours is the complement of it. People don't love beef curry. That's your claim. That's your null hypothesis. You've constructed it, right? Then you're gonna do a test based on that claim, your null hypothesis and your alternative hypothesis. You'll then conclude from that null hypothesis or your alternative hypothesis. Now that's chapter 8 for you, your hypothesis testing. Let's look at this example. An engineer tells this colleague that the variance of the heat caused by the friction between part A and part B is less than 0.5. H naught, we always assume it's true, right? So variance is equals to 0.5, right? Then your alternative is variance less than, you are being told less than 0.5. This is your what you want to test. This is what you claim or what you've been told to claim. You want to test if this is true or not. Then you will conclude on your null hypothesis whether you accept this or you accept this. You accept either one of them. It's either you accept this, you reject this, or you reject this, you accept this. Let's look at this other example. Why did I use this notation? It's because the question, your null hypothesis testing was based on variance. So you use this notation if that's the case. Let's look at another example. A university publicized that 75% of its students complete their degrees within 5 years, right? And I want you guys to understand, you make your null hypothesis based on the parameter, not on the sample. You'll never see H naught and P hat here or H X bar or S here. It's either you see variance squared, P or mu, because the null hypothesis is based on the population, not the statistic. It's made based on the parameter, not the statistic. Right, so this example, a university publicized that 75% of its students complete their degrees within 5 years. So what this is always assumed to be true, right? Okay, also, I forgot to say this. This is looking at one side because it's only pointing this side. So it's a one-sided alternative test, right? This one, they did not tell you less than or greater than, they just said it's within, so it's not equals to. So this one is looking at two sides. It's a two-sided test. This one is a one-sided test. This one-sided test, this is where we find our rejection region. So this determines your rejection region. In this case, our rejection region will be on the left, right? Meaning on this thing, bell-shaped diagram, your rejection region is here, right? If it's like this, it means your rejection region is on two sides, here and here, right? Now we're just learning how to construct the hypothesis test, H0 and H1. Let's look at this nice another example. Your neighbor claims that his rose bushes bloom for on average more than 45 days. We always assume this is true. Greater than, more than, okay, 45, right? Good. It's a one-sided test. meaning our rejection region will be on the right. Right? All right, cool. So 8.2, 8.3. Now we're looking at now, how do we then test this hypothesis test if your variance is unknown, right? Suppose we have a test which is mu is equals to 168, h1 is mu greater than 168. My rejection region is on the right. Right? You then have a sample, a situation where your sample average is given as 171, right? Now you're testing this now, if your average is true. Okay, let me, all right. All right, I'll find an example to make this thing clear. But can you guys make note of this? Type 1 error, it's when you reject H naught while H naught is true. Right? It can also be in a case where you don't reject H naught, but H naught is false. Right? So we have type 1 error and type 2 error. Okay, let's find a nice example. Do I have them here? All right, there we go. There we go. All right, let's look at here. A pharmaceutical company claims that for antibiotic C, the average time till peak concentration is more than 10 hours. You are to check this claim, right? So you're checking a claim. Okay, you randomly choose. So in this statement, guys, you're gonna be told two things. Things based on the population and things based on the sample. You make the hypothesis test based on things on the population. So every time in chapter 8, you will receive a statement. This statement will have a claim. This statement will have two things. It will have information based on the population. It will have information based on the sample. Now, this more than 10, it means this is information based on the population. So they'll start give you information based on the population, then the next information will be based on the sample. You randomly choose 100 patients. Now you randomly choose, this is the sample now. Everything that you're gonna be told now is based on the sample. With antibiotic C and monitor their peak concentration for the sample, the mean till peak is 10.1. So this is X bar, right? This is your sample mean. The standard deviation for the similar antibiotics is 3. You assume this is true for antibiotic C. Use a 1% level of significance to test if the claim is true. Now, right? Step 1, you need to construct your what? Your null hypothesis and your alternative hypothesis. Mu, why mu? Because average, mu, right? We always assume it's true, equals to 10. Why this 10? Because it's the population average, and my null hypothesis is based on population parameters. Right? You said, what is your claim then? You claim is more than, you're claiming that the concentration is more than 10, hence more than 10. From just this, I know that my rejection region is on the right. Right? I'm testing my claim now. Step 2, you need to calculate something called the test statistic. Let's call it TS. Right? How do you go about finding that? You use your Z score, right? You remember this formula here in chapter 5. Chapter 6, rather. Chapter 5 and 6, yeah. So Z naught is equals to X bar minus mu standard deviation over the square root of n is equals to, you are given this 10.1 minus the actual one, right? Your mu, which is your 10, divided by your 3, which you're given as your standard deviation, over the square root of 100. Then your test statistic is equals to 0.33, right? Now let's make a rule. Let's make a rule here. My rule is I will okay, I'm gonna write it down on our chat, the rule. I will reject H naught, which is my null hypothesis, if my test statistic is dash 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 critical region. Right? I will reject H naught if my test statistic is dash 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 critical region. This is the rule. Now let's find the critical region. You told alpha, your alpha, this is alpha now. It's not 1 minus alpha. You're no longer given 1 minus alpha. Even the percentage is very small to be 1 minus alpha. So this is just alpha now. You're given alpha is 1%. So 0,001, right? So your rejection region, so, right? Yes, question.
Say based on like I'm a little bit confused based on the null hypothesis and alternative hypothesis. So if they're saying a company claims that antibiotic C, the average time till peak plasma concentration is more than 10 hours, like that more than 10 hours, isn't it our null hypothesis? Because that is what they claim. And then the alternative hypothesis will be like if it will oppose that by saying it's more than, it's less than 10 hours. Why are we saying the null hypothesis is equals to 10 hours?
Because we always assume our null hypothesis is true. So we say H naught mu is equals to 10 rather than saying it's less than. Then the claim, we put it as our alternative. The
So that,
assumption,
okay,
yeah.
sorry.
So the
No,
assumption of hypothesis testing is that your null hypothesis, you must always assume it's true.
yes, I agree with that. What I was conflicted about is the fact that they're saying it's more than 10 hours. Isn't that more than 10 hours our null hypothesis?
No, that's you want to test that. That's what you want to test. If what you're saying is true. Angithi, I mean, the thing is, you will say our average is 10, right? Is equals to 10. That's a population I mean, the parameter will have, my dear, H naught, the actual average, the population will have its actual average, and you assume it's true, so you say it's 10. Then your what you want to test now, it's what you claiming, that it might not be 10, it might be greater than 10. This is what you saying. You're testing what you saying on what is true,
Mm,
right? We'll
I'm
do
still lost.
no, we'll do some
Um,
other examples. It will clarify some of the things. Yeah.
okay, but can I? Okay, just for the last time, ne?
Yeah.
Okay, so does that mean that? Because from the statement, they're not saying it is equals to 10. They're saying it's more than 10. So in my thinking, I was like, it being more than 10 hours, because that is what they're written, that is what they're claiming. That will be our null hypothesis. And then the alternative one, it will be less than 10 hours.
Why
And
are
that's
you
where we
saying
will
less than?
prove.
Why are you not? Okay, if you think like that, why are you saying less than? Why are you not saying not equals to? Why do you choose less than? Why don't you choose not equals to?
Okay, it can be less or equal. That can be my alternative hypothesis, because my thinking is they gave us that it is not 10 hours. They said it is, and that
Right.
they're saying the average. Okay.
If you if so what you're saying, I get what you're saying. I want you to understand something here. You saying it should be like this, then your alternative be what? Your alternative is what then?
It will be
Greater than.
less. No, they said it's more than, so the null hypothesis they're
Oh, will
saying
be more
the
than. Okay, sorry, it's more than. Then here you're saying less.
or equal to, because yeah.
All right. Then why? Then my question now to you is, why do you prefer to choose your alternative as this and not as the greater or equals to? Because greater or equals to is not included to your null. So what makes you then choose this one and not this one? Because you can still have a claim on this. So with your understanding, it becomes confusion to whether which one to choose. That's why the first thing you do is you assume your null hypothesis to be equals to. Then what you given, then it's gonna be your alternative.
Okay, so what you mean is like the null hypothesis is always equals to, not greater, based on the statement or whatever. And if the statement it says it's more than 10 hours, that more than 10 hours will be our alternative
We're on the
hypothesis.
same page now.
Okay.
Because if you don't do that, you'll have a confusion of now deciding whether to use greater or equals to or less than equals to in your alternative if you don't assume some of the things. All right. So yes, this is my rule. I will reject H naught if my test statistic is dash 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 critical region. Let's find the critical region. So you given alpha as 0.1001. Your critical region, you know it's on the right, it's here, right? For you to find this area to the left, what do? You know that this is, because if I know that this area is 1%, then this area to the left is 0.99, right? So I go to my tables 0.99, 0.99, 2.326, 2.326, 2.326. This is my rejection region, right? Now, let's go back to my rule. Where there is dash, 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 put greater than. Why? Because of this alternative. What is the value of your test statistic? 0.33. What is the value of your critical region? 2.326. What is your rule saying? I will reject H0 if my test statistic in this case is 0.33 greater than 2326. So is 0. Now I'm asking you guys, is 0.33 greater than 2.326?
No.
Then do not reject H0. That's your conclusion. Any questions? Ask me, guys. This is your chance. Ask me anything. H0. Or was it clear? Give me a thumbs up if it was clear. Okay. Thank you, gentlemen. So yeah, do not reject H0. So this is how you conclude there is not enough evidence to conclude that the average time is more than 10%. So this is like a statistical language, because you don't want to put yourself in a situation where you say you reject H0 and you accept H1, because once you do that, the company might collapse. Remember, you are in a management position, so you're in these big boardrooms with big guys in the company. So you can't tell them that you're rejecting H0 and you're accepting H1, because they'll go with your H1 then only to find maybe you're wrong, right? You can never be sure in life. So you leave space for more research, you leave space for error. So that's why when you conclude to your bosses there, your directors, you say, I'm rejecting H0. I'm sure that I do not reject H0, right? And I'm sure of that I mustn't reject the equals to 10. But I'm not also saying we should go with a mu being greater than 10, because we might be in a situation where we don't have enough information to conclude that alternative is true. Because remember, we're doing all this testing based on the sample. So maybe we might need a bigger sample. Maybe we need to do more research. But I'm saying that we shouldn't reject H0. That's how you speak if you're a statistician. Okay. Okay. So then you remember what I told you, right? This thing. You said you did not reject H0. You go a step further. You might be doing what is known as a type 2 error, where you don't reject H0 but only to find that H0 is false. That's called a type 2 error, right? Okay. Let me see if I have another example. How I do 8.2. All right, I have. Okay, so an electronic company has designed a new model of oven that they believe has quicker cooking time than previous models, right? To test their belief, they select 5. So everything now that I'm going to be told is based on the sample. To test their belief, they select 5 new ovens and perform a standard test in which an apple pie is made. The average time is 0.7 hours. The previous models had an average time of 0.82. The previous, meaning the population now, they're talking about the population parameter, and the standard deviation is 0.16. So variance is known because variance is being told on the population level. They assume the standard deviation has not changed and do an hypothesis test using 5% level of significance to confirm their beliefs. What conclusion can they make? So an electronic company has designed a new model, right, of an oven that they believe has quicker. So this new model is quicker cooking time than the previous model. This means that for you to test this, your alternative should be less than, since your new model is quicker. We always assume that the null hypothesis is equals to. We assume the null hypothesis is generated based on the population parameter, which is 0.82, less than 0.82. This less than comes from understanding that you're testing whether this new one is quicker than the old one, right? You then understand, just from constructing this, you then understand that your rejection region is on the left. It's here, right? You're given your alpha as 0.05. Then you calculate what is known as your test statistic. You use this formula here. 0.7 you are given minus your actual parameter mu, which is 0.82 over 0.16 over the square root of 5. Your value is this. Let's calculate now your critical region. Your critical region is on the left. It's here. You will use this 0.05 to find your critical region. If it was here, you were going to say 1 minus this 0.05 to find the area to the left of it, right? But because it's here, you go straight to it, because every time they give you this, you need to know to find your z, you need the area to the left of it. So you go 0.05 to your statistical tables. Let's quickly go to our statistical tables. 0, where are they? 0.05, right? It's this one, minus 1.645. Minus 1.645. Minus 1.645. Can we write that down? There, minus 1.645. What is our rule? I will reject H naught if my test statistic, this is your TS, your test statistic, minus 1.68 dash dash dash, I put this value less than critical region minus 1.645. Now I'm asking you guys, is minus 1.68 less than minus 1.645? Guys, is minus 1.68 less than minus 1.645?
Yes, sir.
So you reject H0,
Yes.
right? So if you reject H0, you then concluding that the new model is indeed faster than the old model. Let's look at another example. Right. A light bulb manufacturer guarantees that the mean life of a certain type of bulb is 750. So this first part is for the population. Everything that will follow now will be based on the sample. A random sample of 36 bulb has a mean life of 745 hours. You assume the standard deviation of the life is 60 hours. Do you have enough evidence to reject the manufacturer's claim? Now, from this statement, you're not being told whether it's greater than 7.5 or less than 750, I mean, or less than 750. So this is a two-tailed test. So it's not equals to, right? Your claim, right? Now, what do? You construct your null hypothesis. We always assume our null hypothesis is true equals to your alternative, which is H1, will be not equals to 750. The first thing you do, you calculate your test statistic, right? How do you do that? You are given this 745 minus 750, which is your population average, your parameter, over your standard error, of which in this case is just 60 divided by the square root of 36 equals to minus 0.45. Now let's find our rejection region. Our rejection region is in two places because it's a two-tailed, right? The first rejection region is alpha divided by 2 and alpha by 2, right? Now, you remember how we founded this. You're given your alpha as 5%. What is 1 minus 5% divided by 2? It's equals to 0.975. 0.975. Then if you go straight to your tables, let's go to our tables. Where are these tables now? Here. If we go to our tables, 0.975, it's 1.960. 1.960, right? If you look at our tables, then since it's a complement of this, so it means that your rejection region is between minus 1.96 and what? 1.960. This is your rejection region. Since it's a two-tailed test, you will have two rejection regions. Now, let's go back to our rule. I will reject H0 if my test statistic is between these two. Now, let me ask you, minus 0.5. Is minus 0.5 between minus 1.96 and 1.96, or is it outside here? I'm asking you guys.
It is within.
Really? It's within, right? So what does that mean? It means that it's within the rejection region. We reject H0. But rejecting H naught doesn't mean you're concluding. Oh, sorry, guys. If you look at your rejection region, right? Sorry, I made some error here. Your rejection region minus 1.96 and 1.4 and 96. If you look at your bell-shaped drawing here, right? This is the area. So minus 0.5 is here. Your rejection region is from minus 1.96 to the right. Another rejection region is on your right, this side. So it's not within your rejection region, so you do not reject H naught, but you also can't conclude on H1. Right. Okay. So any questions? Okay. Now let me explain these other ones now. Detailed formula sheet. This one, no. Not this one again. So detailed formula sheet. One now. Okay, I'll have to find this formula sheet for you guys, but let me see if I have a formula sheet here. Rather do it from there. All right, I think I do. Just give me a second. Oh my. Okay. Maybe what I can do. It's fine. The word. Downloads. Yeah. Okay. Almost done. Save. Okay, cool. Let me share now. Let me share. Okay. Yeah. So that's basically what hypothesis testing is about. So hypothesis testing can then be done within different statistical parameters, right? It's either it can be done with regards to proportion, like I've explained, or else it can be done in average, no variance, right? We always assume that null hypothesis is true. So it's either here you have your mu, your p, or this. We always assume it's true from your mu naught, your p naught here, variance naught here, right? H1, your alternative, it's either still these two parameters, this thing should be the same as your alternative, p or variance. It's either it's greater than, less than, or not equals to, right? What does this mean? It means that your rejection region is determined by your alternative hypothesis test. Reject region, I'm gonna call it reject R, right? It's either it is here, or else it's here, or it's both sides. This is your actual parameter, which can be either mu, p, or variance. Your test statistic, if you're dealing with a question where you're testing or you're claiming your mu, your test statistic is equals to z is equals to x bar minus mu over the variance divided by the square root of n, right? If you're dealing with proportions, your test statistic is what? Z is equals to p hat minus the actual proportion over your standard error, which is going to just be p q all divided by your n. If your hypothesis testing is based on variance, you're looking at your statistic will be n minus 1 s squared o over your chi-square n minus 1 squared 1 minus alpha squared, right? Now you use either, so to find the rejection region for this, you use the chi-square table. To find the rejection region for this, you use the z table. To find the rejection region for this, you use the z table. Then you conclude based on the rule that I've given you, which is rejecting H naught if your test statistic is dot dot. In the dot dot, you put the sign that is in your alternative hypothesis testing. Then you compare it to your rejection region, which is also known as your critical region. Any questions? So that's it for chapter 8. Any questions? I know it's quite a lot to take in one session. Hence, I've given you guys some questions to do in your spare time. If maybe you find questions that you don't understand, you book a one-on-one session, then I take you through them. Yeah, then, I mean, you'll better understand with questions. I mean, more practice comes with a lot of understanding as well, you know. So I encourage you guys to just do questions, do your past papers, do more questions, right, to understand any concept of stat. That's how you'll be able to even get good grades out of your modules. So yeah, Bulelwa, any, if we don't have questions, then that's it for today.
Thank you, Mr. Ngcobo. Yes, if there are no questions, then it means we'll see you next week.
Are there any questions, guys? Okay. If there are no questions, please do the assignments. If ever, maybe you might record the slides, liaise with Bulelwa. I mean, if one-on-one session, Bulela will help you on that. Besides that, it was a great session. I'm happy that you guys joined. Enjoy your rest of your weekend. See you guys next week.
Thank you, Mr. Ngcobo. Bye, guys.
Okay, bye, guys.
Bye bye.